All right, for example 2, we are dealing with another parametric equation, and it says, when is the particle at rest? Typically, we would say a particle is at rest when the derivative is 0, because derivatives represent velocity, and when your object is not moving, the velocity of that object would be 0. And that is the case here as well, except when you're dealing with parametric equations, you have to find when both the x derivative is 0 and the y derivative is 0. So you kind of have to find a point where they have a common time value that gives both of these derivatives a 0 solution. Anyway, so mathematically, what do? You're going to take derivatives, obviously. Start with the x equation. I'm going to get 3t squared minus 6t minus 9 for my derivative. Set it equal to 0 and start solving. And when you're solving, you should just be factoring out. You can factor out a 3, and then you're going to factor the rest. I believe I've got this right. So I'm getting t equals 3 and t equals -1. So at both of these time values, the particle is at rest, but only in the x direction. It could still be moving up and down, but in the horizontal direction, it has stopped at 3 seconds and at -1 seconds. But we got to look at the y equation as well. So the derivative of the y equation is 3t squared minus 15t plus 18, I believe. Set that equal to 0. Same deal, factor out a 3. I think you can still do factoring for the rest of that trinomial there. Minus 3, t minus 3, t minus 2 should do it. And so we get t equals 3 and t equals 2. So this means that the particle in the y direction, so in the vertical direction, is not moving at 2 seconds and not moving at 3, meaning it's not moving up and down at those times. But we want to see what they have in common as far as when the object is completely at rest. So the only time that it's completely at rest is when it is at 3 seconds. So you're just going to ignore these two guys here. Okay, so the particle is at rest, fully at rest, at time 3. Okay, these equations on this slide shouldn't be anything surprising to you. It's just rewriting derivatives. I actually think in our notes we didn't do third derivative. It doesn't look very much different than the second derivative equation, but there's your derivatives again if you need them. Example 5 says find all points, if any, of horizontal and vertical tangency to the curve. So when you are looking at just a generic derivative for a parametric function, you do dy dt over dx dt. That's how you compute it. A horizontal tangent line is going to occur when the numerator is equal to 0. So we have a horizontal tangent line when dy dt is equal to 0. And then we have a vertical tangent line for a parametric function that will occur when the denominator is equal to 0, and that means in this particular case, dx dt is equal to 0. So we're going to need derivatives again. We'll start with the horizontal tangent lines. So I need to find dy dt. And that is the derivative of only the y equation, which would be 3t squared minus 3. And I need to find when that would be equal to 0. So it's pretty easy. Just set it equal to 0 and solve. And you are getting, I am getting plus or minus 1. So I'm getting 2 different times when there is a horizontal tangent line. Now, read the directions again, because it says find all points when you have these horizontal and vertical tangent lines. What I just found is not a point, that's a time. So in order to convert that to a point, you have to take each of those time values that you just solved for, and you're going to plug them into the parametric equation for x and y to find the location of that point when the time is -1, when the time is +1. So for the first value, when I plug in -1, when I plug in -1, I am getting, what would this be? The x was 3, and I think this would be 2. So there's a point at the point 3, 2. We have a horizontal tangent line, and then we have another one that we need to find the location of at time 1. So again, plug 1 in to each of your equations and solve, and you get 5, -2. So you have at 3, 2, you have a horizontal tangent line, and at 5, -2, you have another horizontal tangent line. Okay, let's continue. So a vertical tangent line, this is going to occur when dx dt is equal to 0. So we need to find dx dt. Dx dt is 1, which means it's not possible for dx dt to ever equal 0. So therefore, there are no vertical tangent lines. Okay, it does say use a graphing utility to confirm your results. So here is what the graph of the function looks like. And I do not see any locations where I would have a vertical tangent line, but I do at 5, -2, and at 3, 2, it does appear that we would have horizontal tangent lines in those locations. All right, last question in relation to just regular derivatives is asking about concavity. So for concavity, remember that that is directly tied to a second derivative. So what we're going to do first is we're going to find the first derivative, which means dy dt over dx dt. dy dt would be negative sine, dx dt would be cosine, which I could simplify and just call tangent, negative tangent. And then for the second derivative, to do this, you would take the derivative of the derivative, which is negative tangent of t, and you would divide by dx dt. So the derivative of the derivative is, let's see. This would be negative secant squared t, and then dx dt is cos of t, and I think we could rewrite this. Secant squared is 1 over cosine squared. You could throw the negative up there rather than the front, divided by cosine. And if you do outer inner, you would get negative 1 over cosine cubed t. That would be totally simplified. Okay, there's your second derivative in its most simplest form. So what we would do to find a point of inflection is we would be looking for either when the derivative is equal to 0 or when the derivative does not exist. Okay, so I can show you both. If you take your derivative, second derivative, and set it equal to 0 and start to solve, you're going to find that you're not going to get an answer. It's not solvable, I guess. Not solvable because -1 divided by, it can't be divided by anything to get 0. However, it is possible that this derivative does not exist because cosine could possibly equal 0. So we're going to solve and find that value because that could also be a point of inflection. So you would cube root both sides, but that's still going to give you 0. So when cos of t equals 0 is like asking when is cosine 0? That occurs at pi by 2, 3 pi by 2, etc. But we do have an interval, a time interval from 0 to pi. And so pi by 2 would be the only thing that fits in that value or that interval. And then you make a chart. Okay, and so you could put pi by 2 here. I think we did more of a chart format last year, but this works too. This is a little simpler. I don't want to make it go to infinity because we do have a restricted time interval of 0 to pi, and I don't think it was inclusive either, so I'll go ahead and put open circles. This is at 0, and this is at pi. So I need to then choose a value that is between 0 and pi by 2. Let's say pi by 4 would work. And I'm going to plug that into my second derivative to see whether it would be positive or negative. So I'm going to go to my second derivative right here. Cos of pi by 4 is radical 2 over 2. If I cube that, it's still positive, but then I divide by a negative, and so I get a negative, which means that my function would be concave down in that interval. And then I can do that again for 3 pi by 4, maybe something between pi by 2 and pi. Cosine of 3 pi by 4 would be negative. Radical 2 over 2 cubed would still be negative. Divided by the -1 on top would make it positive. So that would be concave up from pi by 2 to pi. So concave down would be from 0 to pi by 2. And then concave up would be from pi by 2 to pi. So that means that pi by 2 is a point of inflection.